Okay, so for the second talk today, I'm going to have JD Quigley, who will be telling us about free incomplete temporal functors are almost never flat.
Okay, thanks for the introduction and the invitation. So I'm going to talk about a project in equivariant algebra studying free incomplete Tambara functors. So let me just get, and this is joint work with Mike Hill and David Murley. And throughout the talk, all the groups are assumed to be finite. So I want to start with the theorem from ordinary algebra, which is more of like an exercise from your first abstract algebra course. So the theorem is that free commutative rings are always flat as abelian groups. So this is a pretty useful fact from classical algebra. Maybe I'll give an example. The free commutative ring on one generator is a polynomial ring on one generator. And as an abelian group, this is just Z with generators 1, x, x squared, and so on. So why is this flat? Well, it's actually free, and free implies flat. So today I want to tell you about the equivariant version of this statement. And I'll start with a slogan, which is that in equivariant algebra, the analog of abelian group is a Mackey functor. And the analog of commutative ring is an incomplete Tambara functor. So I want to give a lot of examples of these objects and define them in a moment. But with this slogan in mind, let me state our main theorem. Which is really just the title of the talk with a couple extra words. So free incomplete Tambara functors are almost never flat as Mackey functors. And so while I have both these statements up, let me just highlight the difference. In the classical setting or non-equivariant setting, free commutative rings are always flat. And in the equivariant setting, we're saying that these analog of free commutative rings are almost never flat. So I think this is a pretty weird statement. So my goal today is basically to explain what all the words in this theorem are, give a few examples, maybe some connections to equivariant stable homotopy theory, and then sketch the proof. So before I give any precise definitions, let me give two examples of the types of structure we want to capture with Mackey functors and incomplete Tambara functors. So the first example comes up in ordinary algebra. And if you were in Birgit's talk right before this, you've actually seen some of this. So let's let M be a G module. Here, G is just some finite group. Then we can record the following information. And throughout the talk, I'm going to assume K is a subgroup of H, and H is a subgroup of G. So we can record the fixed points of M with respect to the action of any subgroup. So maybe something like this. And there are each of these fixed points has an action, a residual action by a Weyl group. So if I take the fixed points with respect to the trivial subgroup, that's just M. So this has a G action, which I guess I can write as the Weyl group of E and G. Here I have a WGK action, and here I have a WGH action. So I can keep track of some of this structure. And I also have maps comparing the various fixed points. So one map is the transfer. The other is the restriction. And what are these maps? So the restriction from K to H, from H to K, is just going to be the inclusion of fixed points. So K is smaller than H, so it fixes more elements, or at least as many elements. The transfer, which I think was called the norm in Birgit's talk, goes from the K fixed points to the H fixed points. And what this does is it takes a K fixed point, call it M, and sends it to the sum over the elements in the Weyl group of K and H of gamma times M. So this produces an H fixed point for us. So this is the type of structure I want to capture with Mackey functors or abelian groups. If I want some extra multiplicative structure, I can ask that M be a G algebra so that I can multiply elements in M. Then each of these fixed points becomes a ring. And I can define one other map, which I'll call the norm from K to H, defined exactly like this transfer. But instead of taking the sum over the Weyl group, I'll take the product. So this is one example of the type of data I want to keep track of with a Mackey functor or a Tambara functor. Before I give the precise definition, let me give one more example that's going to be important for the talk. So maybe the most important example is the Burnside-Tambara functor. Which I'll denote by A underline. And so what sort of data was I keeping track of up here? I'm assigning some Weyl group module to each subgroup, and then I just have these restriction, transfer, and norm maps. So this Burnside-Tambara functor, whatever it is, I have to tell you what it does on a subgroup of G. And if I evaluate this on H, I'll just get the Burnside ring of H. Which I can obtain by taking the monoid of isomorphism classes of finite H sets. That's a monoid under disjoint union. And I can define a multiplication on the group completion using Cartesian product. So that's my Burnside ring. And I can say explicitly what the restriction, transfer, and norm maps would be. So the restriction is supposed to take an H set, say S, and it will send it to the same set, just regarded as a K set. So remember, my convention is K is a subgroup of H and H is a subgroup of G. The transfer is given by induction. So now I'll take a K set and I can produce an H set by taking the product of H with S over K. And then finally, the norm will be defined using co-induction. So I again start with a K set, and then I'll send that to the set of K equivariant maps from H into S. And I guess I didn't specify a Weyl group action, but in this case, the Weyl group is going to act trivially at every level. So I just won't say anything about that. Okay, so these are the sorts of data that we want to capture with Mackey functors and Tambara functors. These naturally show up in like group cohomology. And I'll say in a second, they also show up in equivariant stable homotopy theory. So maybe I'll give a working definition at this point. So for this talk, again, G is a finite group. I'll say that a G Mackey functor and I'll always underline my Mackey functors or Tambara functors. So a G Mackey functor M consists of the following data. First of all, I should have a Weyl group module, WGH module, M of H for each subgroup H and G. And then for a Mackey functor, I just ask for these additive structures. So a transfer map and a restriction map. So the restriction will go from M of H to M of K. And the transfer goes from M of K to M of H. And I ask for these structure maps for all K, a subgroup of H, a subgroup of G. So my G Mackey functor consists of this collection of data subject to some conditions or satisfying some conditions. So these conditions are not really important for this talk. You can kind of imagine what they would be based on the first example. So I should ask for some sort of equivariance of the restriction and transfer maps. I should ask for some sort of double coset formula and things of that nature. Okay, so these are my analogs of abelian groups. And as I mentioned, these naturally show up in equivariant stable homotopy theory. In particular, if I take a genuine G spectrum, X, then I can take its equivariant homotopy groups, phi naught of X, and these assemble into a Mackey functor. I'll use MF to abbreviate for Mackey functor sometimes. Okay, so these things naturally show up. I still have to tell you about the norms. And it turns out that sometimes I want to keep track of all of the possible norms. Sometimes I won't have all the possible norms. And so I need a way of parametrizing which norms I'm going to keep track of. So there's several ways to do this. I'm going to follow a nice idea of Jonathan Rubin, as far as I know. So a G transfer system O is a subgraph of the subgroup lattice of G where I regard sub G as a graph by saying I have an edge from K to H if K is a subgroup of H. So a G transfer system is a subgraph of sub G satisfying three conditions. First, it should satisfy a restriction condition, which says that if the edge k to h is in my subgraph or my transfer system O, and M is a subgroup of H, then K intersect M to M is also in my transfer system. Second, I should be able to compose edges in here, which are supposed to correspond to norms. So if I have some edge L to K and another edge K to H, then their composite L to H should also be in my transfer system. And then finally, I should ask for some compatibility with conjugation. So if K to H is in my transfer system and G is an element in my group, G, then GK G inverse to GH G inverse should also be in the transfer system. So I'll just say out loud, these transfer systems are a way of keeping track of which norms appear in your Mackey functor or your incomplete Tambara functor. And there are several other ways of keeping track of that information. So the keywords, which I'll say for the recording, are indexing systems, indexing categories, and n-infinity operads. But I don't want to go into the details of that stuff. Okay, so let me give a couple of examples of transfer systems, because I think there is some interesting combinatorics to do with these. So one example is I have the trivial transfer system, O_triv. And this is just going to have the edges from a subgroup to itself. All subgroups. So this O_triv is saying that I don't have any non-trivial norms. The next example is the polar opposite. So the complete transfer system, O_complete, is just going to be the entire subgroup lattice. So concretely, this has every possible edge. And for Tambara functors, this will be like our first and second examples, where I have norms between every possible assignment. And to be a bit more explicit, let me give you some examples of transfer systems for small groups. So if G is a trivial group, then this smallest possible transfer system, O_triv, is equal to the largest possible transfer system. And explicitly, both of these just look like a single vertex, and I'll just suppress all the identity edges. More interestingly, if G is, say, cyclic of order P, then O_triv looks like this subgraph with no edge between E and CP, and O_complete is the subgraph where I do have an edge from E to CP. And so you can see that one of these is strictly contained in the other. So these are actually different, and these are the only two transfer systems for this group. I'll give one more example. If G is CP squared, then there are 5 total transfer systems. So some examples are O_triv, O_complete, which has all the possible edges. And you can check, for example, that the subgraph where I just have an edge from E to CP is a transfer system. So a couple of fun exercises if you're already bored. One is to find all of these for CP squared. And then a second exercise is to find all of them for CP cubed. So the second exercise is actually a little bit cruel, and I want to mention this because I think it's an interesting computation in homotopy theory. So the transfer systems for cyclic groups of prime power order have been enumerated by Balchin, Barnes, and Reutzheim. And they show that the number of transfer systems for Cp to the n is the n plus first Catalan number. So for Cp squared, we had 5. If you do exercise 2, you have to find 14. And if you go to Cp to the 4th, you have to find 42. So these transfer systems get a little bit complicated. And I think in general, it's a hard problem to try to enumerate them for general groups. Okay, so these transfer systems are going to parametrize norms. So now I can make a definition. I think this goes to work of Blumberg and Hill. An O Tambara functor R underline consists of the following data. So I want some multiplicative structure. So this is like a Mackey functor with multiplication. So first, I should ask for an algebra over the Weil group, R sub H, for each subgroup H and G. I should also ask for the same sorts of Mackey functor structure maps. So I should have restrictions and transfers for all K and H and G. And then the way this really differs from a Mackey functor is in the norms. So I ask that I have a norm from R of K to R of H for all edges K to H in my transfer system O. So this is the sense in which the transfer system is parametrizing norms. It's telling me which norms I'm allowed to, I want to keep track of. So this is an O Tambara functor. And then the terminology is that an incomplete Tambara functor is an O Tambara functor for some O. Okay. So again, I want to connect this to equivariant stable homotopy theory. So 2 examples. I've already seen that if X is a genuine G spectrum, that its pi naught is a Mackey functor. If this is also an E infinity algebra, and here I just mean E infinity in like the classical sense, then pi 0 of E, of X, is an O triv Tambara functor. This is also sometimes called a green functor. And by sometimes, I guess I mean always. So I don't want to go into this too much today, but there are different notions of E infinity in the equivariant setting. And maybe the strongest notion you can have is sometimes called GE infinity. And in this case, phi 0x is an O complete Tambara functor. And this is usually what's just called a Tambara functor. So all of this extra structure actually arises in equivariant stable homotopy theory. And maybe that's one of the main reasons we want to understand it at an algebraic level. Oh, that's a good question. Is R of H assumed to be a commutative algebra? Let me just throw it in. I think it should be. Thanks. Yeah, for this talk, I want everything to be commutative. So I'll assume that. Yep. Okay. So I gave this slogan at the beginning to say that incomplete Tambara functors are commutative rings in equivariant algebra. So let me try to justify that slogan. So let's say Mac G is the category of G Mackey functors. This category is symmetric monoidal. It's also nice in other ways, like it's abelian. But in particular, it's a symmetric monoidal category. And the tensor product is what's called the box product. And you can define this just like you might define a smash product in a nice category of spectra. It's just some sort of left Kohn extension of the tensor product of abelian groups. But all you need to know for this talk is that it exists. And the unit for this is the Burnside Tambara functor. So A box with M is M for all Mackey functors M. Okay, so what's a commutative monoid here? A commutative monoid in this symmetric monoidal category is an O-triv Tambara functor. This is something you have to work out. So that might tell you that O-triv Tambara functors should be thought of as commutative rings. But we can also incorporate equivariance into the notion of monoid. So let me just write down an attribution. I think for cyclic groups, this goes to work of Maser. And then for general finite groups, it's work of Hoyer. I can talk about G commutative monoids in this category, and the G commutative monoids are O complete Tambara functors. So if I want to seriously keep track of equivariance in my commutative ring structure, I have to keep track of these norms. Okay, so that remark is just to explain the slogan from the beginning. And now I think I can define the next word in the title. So definition, a Mackey functor M is flat if the functor M box with whatever is exact. So this is just like how you define flatness in ordinary algebra. Okay, the trick with the long title is that it means I'm going to spend most of the talk just defining the words. So I can finally finish defining the words in the title now. So the last word is free. So how do you define freedom? Well, in this talk, let me fix a group G and a G, let's say fix G, a subgroup H, and a transfer system for G. O. The free O Tambara functor on a generator at level O, sorry, at level H, which I'll denote by A, O, X, H, is the O Tambara functor, which represents evaluation at H. So in other words, if I look at Ham in O Tambara functors from this free O Tambara functor into some other O Tambara functor R, this is just the value of R at the subgroup H. So maybe a nice exercise is to check that if G is trivial, this is just giving you a universal property for a free commutative ring on one generator. Related to that, if G is trivial, so H also has to be trivial, and O has to be, well, trivial, then we can say explicitly what this looks like. So A, O, X, E, I only have to tell you what the value is on one group, namely E itself. And this is just the free commutative ring on one generator. So if I just restrict to a trivial group, I'm recovering classical algebra. In fact, there's a whole family of pairs of H and O, for which I basically just get something that looks polynomial at each level. So this was worked out by Blumberg and Hill. So if G is arbitrary and H is equal to G and O is trivial, so I'm looking at a free green functor on a generator at the top level, an A O triv XG is isomorphic to Z adjoin X tensored with A. And I see a chat here a bit confused about the definition of AOXH. Isn't the data of R the Tambara functor? So I haven't really defined AOXH. So there is a way to explicitly define AOXH, but it required a little bit more setup that I didn't have time for.
Thanks.
Yeah, thanks for the question.
Could I maybe ask a related question?
Sure.
In this universal property, sort of universal property you've given before, is this an isomorphism of sets, abelian groups, rings?
That's a good question. I'm not sure.
It's
Definitely,
rings, right?
I guess so. I guess it is rings. Yeah. Thanks, David. Okay. Yeah, thank you.
So I claim the Hom is always ring valued in O Tambara functors. I mean, how would the left-hand side have a natural ring structure otherwise?
How would the left-hand side have a natural ring structure? Okay, I'm not sure about this.
I guess the free O Tambara functor might be a comonoid.
That sounds.
Yeah, it's a co-ring object in the category of O Tambara functors.
Okay. So this is a co-ring, and so Hom out of it, it's a ring structure. Is that the point?
Yeah, yeah.
Thanks. Yeah, thank you for the clarifications. Okay. Going back to this example, I just wanted to point out that if I take a trivial indexing system, trivial transfer system, and put my generator at the level of the group, I just get something that looks polynomial. I guess one remark I wanted to make, which I'll just say out loud. Sorry, let me skip the remark for the sake of time. Okay. So far I've just given you fairly simple examples, or simple looking examples of free incomplete Tambara functors. I just want to mention that in general, these can be quite wild. So this is also a computation of Blumberg and Hill. If you turn away for a second, I can paste it in. So here I take G to be the cyclic group of order 2, O to again be trivial, but instead of taking H to be G, I just take H to be a trivial subgroup. And in this case, I get something a bit more complicated looking. So downstairs, I get a free C2 ring on one generator, but upstairs, I get some large thing where I just sort of had to freely adjoin transfers for everything downstairs. So I'm not saying what all the structure is here. I just want to indicate that these free incomplete Tambara functors can be a bit messy. Okay, so now I think I'm ready to talk about the main theorem. So the main theorem is describing when free incomplete Tambara functors are flat, and it's saying that it almost never happens. So you can kind of imagine that based on what I've written here. There's no reason to suspect that this crazy looking ring is flat, even in this more complicated category. So what we do to prove the main theorem is we actually give necessary and sufficient conditions on H and O for this thing to be flat, at least when G is solvable. So I want to tell you the two directions of that result. So first, I'll tell you the sufficient conditions. So if 1, there's a norm from H to G in my transfer system, and 2, if I forget about all of the edges in my transfer system above H, I just have something trivial. So in other words, there are no edges of the form L to K in O, with K a subgroup of H. So if my transfer system has this particular structure, then the free incomplete Tambara functor, or the free O Tambara functor on XH actually is flat. In fact, it's actually free as a Mackey functor. And I think I have time to sketch the proof. So the proof uses the norm in Mackey functors and Tambara functors. So under these hypotheses, we can identify the free O Tambara functor as the norm from H to G of the restriction to H of A, O, X, H. But then what is this thing? Well, this is the norm of, maybe I'll write it like this. So the Burnside-Tambara functor for the group H, then I take the free green functor on a class in level H. So then the point is, this is exactly something of this form. And so what does that look like? It really just looks like the Burnside ring or the Burnside-Mackey functor tensored with a polynomial algebra. So this is actually free as a Mackey functor. And then the norm preserves freeze. And then finally, free implies flat. Okay, so basically what's the idea here? We start with our free incomplete Tambara functor, and then we use the norm to reduce to something where we know it's flat or free already. So I've got a couple minutes left. Let me tell you about the other direction of the theorem. So let's suppose, on the other hand, that AOXH is flat. Then we can say two things. First of all, IH upper star O is O triv. So this is exactly condition 2 from the previous theorem. 2, H actually has to be a normal subgroup of G. And if we assume, moreover, that G is solvable, then also we can conclude that there's a norm from H to G in O. So let me zoom out for a moment. So putting these together, we have that if G is solvable, the conditions that IH upper star is O triv and H to G is in O are necessary and sufficient for this thing to be flat. Oops. And this gives you a really sharp upper bound on the number of these that can be flat. So in particular, if G is solvable, there exists at most one subgroup H in G for each transfer system O, such that AOXH is flat. So you can bootstrap this corollary to actually prove some asymptotics for all finite groups. And in the last minute, I just want to show some tables. Oh, if I can share that. Of when these things are free and not. So of course, for the trivial group, it actually is free. Now in these tables, I have the transfer systems listed on the left, and the subgroups appear as what's being quotiented by. So for CP, we have the 2 that we mentioned earlier, and we see that half of the time we get something free or flat, and the empty boxes means it's not flat. And I'll just scroll through these. So for CP squared, Here's the answer to the exercise, the 5 transfer systems, and you see 4 out of the 15 are flat, the other 11 are not. I'll just quickly go through it. So you can see as the group gets bigger, here's CP cubed, these tables get more and more sparse. Here's CPQ, and then here's D6. So the idea is as the depth of the group gets large, this table becomes basically empty. Okay, I'm a minute over, so I'll stop there. Thanks.
Thank you, JD. Let's thank JD for his talk. I'm going to stop recording first.